Yeah, it's okay. So section 3-2 is now going to be called Solving Systems Algebraically, which follows up perfectly from section 3.1 because right away jumping into some recall, in 3.1 we saw that if we wanted to discuss a linear system and what the situation is with the solutions or solution, remember, a system of two linear equations would have either one solution, if the graphs of the lines were destined to cross at one point, which is most of the time, I guess. But you could also have no solutions at all to a system of two equations, and you could also have infinitely many, which, since it just popped into my head, I'll say it. I don't even know if I addressed it in class or in any videos leading up to this, but when we say that there could be infinitely many solutions to a system, that doesn't mean that anything is a solution. All right, I hope that makes sense. Sometimes when there are infinitely many, I might as well be thorough here. So again, this lesson has come to a screeching halt, and we're kind of going off on a tangent here. But don't worry, we'll pick up again soon. So let's say you had 3x plus x minus 5 equals 4x minus 10 plus 5. And so we are going back to the days of just a single variable equation and solving for that variable. If you let this equation play out, again, don't write this down, you would end up figuring out that there are infinitely many solutions to this equation. And not only that, every single number is a solution, which of course that means that there's infinitely many. Okay? Okay, again, there are infinitely many answers to this equation because all numbers are solutions. Literally everything would work when you plug it in for x. But with a system of equations, like let's say you had, let's say your system ended up being like y equals 3x minus 2, and the other equation was basically also 3x minus 2, or probably given as like something in disguise, but it's basically the same thing. This system has infinitely many solutions, but that doesn't mean that every single xy pair is a solution. Does that hope that makes sense? There can be infinitely many answers, but not everything is an answer. Like 0, 20, okay, or 0, 55, or 3, 55. You know what I mean? Those are examples that are not solutions to the system, but yet there are infinitely many solutions to this system. So I hope that makes sense. So anyway, getting back on track. Oh boy, I almost feel bad about going off on a tangent like that. But getting back on track, you can have a single solution. You could have no solutions at all, or infinitely many. And in section 3.1, we saw that if we wanted to discuss, or figure out what was going on, we would need to graph both lines, because in section 3.1 we investigated the graphing method. But question, can you think of any drawbacks or disadvantages to the graphing strategy? Graphing both lines to see where they might cross, and therefore what the solution would be. Now, if you're at home right now because you missed class for whatever reason, you probably don't realize that we just in class before this did an activity that's sort of like flushed out maybe a couple, like at least one of these reasons, and we sort of investigated why the graphing method could sometimes be unreliable. Okay? So can you think of any drawbacks? Well, one reason is, what if the lines cross somewhere messy? I mean, that's possible. You know, lines don't have to cross at like nice integer coordinates. You know, a line could cross, or two lines could cross at, let's say, 3.71 comma negative 8.05. I mean, that's unlikely, I guess, in high school problems, but it's possible. So, and if that ends up being the case, how are you supposed to know that? Like, if you look at two lines crossing at a weird place, how are you supposed to figure out exactly what the answer is? And another reason is, what if your lines are going to be crossing like really far away from the origin? You know, your graph is only so big on your paper, right? Like, again, it's not likely in most high school math problems, but I mean, it is possible that two lines could be destined to cross at, like, 387 comma negative 502. So again, on a normal piece of paper, on normal graph paper, I mean, that doesn't sound ideal to figuring out what the answer is just by graphing those lines. So those are I think those are the two major reasons. Once again, I'm not knocking the graphing method. The graphing method will work just fine in most situations, but ultimately it's not the most reliable. And, so there's got to be a better way, which of course there is. Behold, the substitution method. It's one of our algebraic methods. We're not going to use graphs, we're going to use algebra. So here's an example. 4x plus 3y equals 4 is my first equation. Y equals 2x minus 7 is my second equation. And again, not to be insanely repetitive here, but it is very possible that on a normal piece of graph paper or whatever, you could graph both of these lines just fine and end up being very certain where they are crossing, if they cross at all. But of course you'd have to solve this equation for y. But Anyway, so here's how the substitution method works. It's more reliable overall. Yep, we actually have what I'm going to call step 0. Step 0 is make sure one of the equations is solved for a variable. In order to do the substitution method, we need to know what x is equal to or what y is equal to. One of the equations has to be telling you that. So, okay, again, one of the equations has to be telling you what x equals or what y equals. In this case, the second equation is literally telling you that y equals 2x minus 7. Y is equal to 2x minus 7. Y is all by itself on one side, and so it's solved for y, and we know that it's equal to 2x minus 7. Step 1 is to substitute. I guess I got to go with a blue color here. Substitute that equation into the other one. So the fact that we know that y equals 2x minus 7, well, look in the other equation. I mean, that's a y. The other equation has a y. And therefore, since we know that y is literally equal to 2x minus 7, we can replace or substitute 2x minus 7 in for the y. So the first equation becomes this: 4x plus 3. Now, instead of writing y, like here, since I know that y and 2x minus 7 are the same thing, I can write that, and then I can finish writing it with equals 4. So again, make sure you look at this and understand that this is the first equation, except we've substituted 2x minus 7 in for the y. We've replaced it because they are interchangeable. They are equal to each other. You know, like the second equation was literally telling us was the case. Step 2, I mean this, and this is the money step, step 1. I mean that is the namesake step. You know, that's why we call it the substitution method from this very step. Okay. Step 2, solve that new equation. See, the brilliance of this strategy is once you do this step, now you actually have an equation you can solve. It's only got one variable, you know, this new updated sort of equation. So now you can solve it. So the first thing would, you know, to solve this would be, of course, clearing the bubble by the distributive property. Okay. So this becomes 4x, excuse me, and then the distributive property gets me, oh, that looks too much like a you-know-what, 6x minus 21 equals 4. So of course I'm going to combine these like terms that are already together on the same side here, and then I'm going to like add 21 to the other side, so I get 10x equals 25. And then when we divide both sides by 10, I believe I should grab a calculator, I guess, but I'm like 99.999% sure that it's going to be x equals 2.5. All right. So again, look, not completely ugly, this x coordinate of the solution, but you know, not perfectly nice. So maybe the graphing method would be, you know, a little you know, inconclusive. If you're looking at that going, I think the x coordinate is 2.5, but am I positive? And so, you know, this substitution method is ultimately going to be more reliable overall. And then guess what? We're not done. Step 3, what do we still need to do? We know what x equals, but don't we also have to figure out what y equals? So we're going to use that solution to solve for the other variable. We're going to solve for y, and we might as well use the fact that we now know what x equals to our advantage. So I'm going to go with like the fact that y literally equals 2 times x minus 7, but now I know that x is actually 2.5. So y equals 2 times what I just realized was 2.5 minus 7. It's this second equation, but now we know x is 2.5. So y equals 2 times 2.5 is 5. And then 5 minus 7 is negative 2. So the, it's probably better if I bring those y's down. So your final answer is 2.5 comma negative 2. X equals 2.5, y equals negative 2. And if you were to graph those lines on a grid or in graphing paper or whatever, you would see that they cross there at 2.5 comma negative 2. Let's just do a couple more examples or whatever. And we have this, so here we go. There's going to be a little bit of a plot twist here. 2x minus 3y equals 6 is our first equation. X plus y equals negative 12 is our second equation. Now, going by the steps, what was step 0? Step 0, before we do anything, we got to make sure that we know what x equals or we know what y equals. One of the equations has to be telling us what x equals or what y equals. And in this particular example, neither one of the equations is doing that. So in order to satisfy step 0, we have to actually solve one of these equations for something. And based on you want to choose the easiest path, like the least complicated path possible. You want to be very smart about which equation you choose to solve for and what you solve it for, x or y. When I look at this system, what do you think? Do you think I should solve the first equation for x, solve the first equation for y? Should I solve the second equation for x or the second equation for y? I mean, what do you think would be like the least painful, the least messy choice? Well, I mean, I'm looking at equation 2, and I think it's kind of a horse apiece, solving for x or y. I mean, right? I mean, think about it. Can you imagine solving the first equation for x or the first equation for y? It's at least more steps. Okay, it's at least more steps, and you're probably going to end up with like a messy fraction or something along the way. So, how about we solve the second equation for x? And to do that, I'm going to subtract y away from the left side, and it's going to, to keep it balanced, basically we're subtracting y from both sides, right? So I end up with x equals negative y minus 12. I don't know, I just would rather put the variable there first. You could have written negative 12 minus y. So now I know what x equals. Now I know that x is literally the same as negative y minus 12. So I can take that negative y minus 12 quantity and substitute it in for the x in the other, it's got to be the other equation. Whatever equation you solve for, whichever equation is telling you what x equals or what y equals, you got to plug that into the other equation. Otherwise, you're going to just be, it's not going to get you anywhere. Okay, just a long story short. So here we go. Now the first equation becomes 2 times x, which we now know is equivalent to, and again, it's the entire quantity. It's 2 times the entire quantity that is x. So make sure you use parentheses just like I did in the last example. And then we have the minus 3y equals 6. So that was the money step. That was substitution. Now we actually can solve for y. So I distribute, and I get negative 2y minus 24 minus 3y equals 6. And so these two terms will combine to be negative 5y. See, now I'm just in solving for y mode. Ever since this step finished, I now just find myself in, let's solve for that y variable. Adding 24 to both sides would leave negative 5y over here, and over here it would become 30. Yep. And so when we divide both sides by negative 5, y ends up equaling negative 6. So now we can take that answer and plug it in somewhere, and it really doesn't matter where. I'm probably going to choose this equation right here, but you could choose the original second equation. You can choose the first equation. It doesn't matter. If you know that y equals negative 6, now you can plug it in for a y somewhere and figure out x. The other half of your final solution. So remember, negative and then the y. negative, and then the fact that y equals negative. So we have negative 6. So so this is basically a positive 6. And so, interesting. Funny coincidence. Turns out that x is also equal to negative 6. So our final answer, you can summarize it this way. This is very common. Negative 6, comma, negative 6. I believe one more example, but plus a bonus sort of thing. So example B, this one, if I were you, I would try this on your own at home. Pause and try this one on your own, because I don't think there's any crazy new plot twist to this one. So pause the video, try it on your own, and unpause. Okay, so here we go. Once again, you had to actually solve one of these equations for x or y, because again, you got to know what x equals, you got to know what y equals. When I look at what would be my easiest path, I choose solving the first equation for y. So if you add the y over, you end up with 3x equals y. Or in other words, just kind of reverse that. Y literally equals 3x. So now I know what y equals, and I can plug it into the other equation. I can replace that y with a 3x. So I'm going to do that. 4x plus 3 times 3x equals 26. Now I find myself in a just solving for x mode, because this is now an equation that I can solve for something, solve for x. 13x equals 26. Divide both sides by 13. I guess I have the space here to actually write that out. That work. So cancel mania. And that should just be 2. So x equals 2. And so y literally equals 3 times x. I now know that x equals 2. So y equals 6. All right? And so you can summarize, of course, your final answer as 2, 6. Now, one more sort of thing. I'm going to assume you have space somewhere to kind of write this down. I don't think I'd be giving you the full story. I mean, it's not like life or death or anything, but you could have and again, I'm just going to assume you have more space than I do, like in a margin or something. I don't think you're going to need a whole lot of space, but example C, y equals, negative 2x plus 1, and then like y equals, negative x minus 5. Okay? I just want to point out really quick that if you have a system like this, which is not exactly rare, okay, both of these equations are solved for y. Okay? So from the beginning here, we were saying like step 0, you need to know what x equals, or you need to know what y equals based on one of the equations. Well, here we go. Look at this. Both of these equations are telling you what y equals, which is an extra good thing, because when you actually go ahead and do the substitution method, whether you whether you substitute this negative x minus 5 into that y variable, or you substitute this whole negative 2x plus 1 in for that y variable, either way will get the job done. But I think a lot of teachers, and maybe even textbooks or whatever, refer to this as, if you have both equations saying y equals whatever, you can just set those equal to each other. So this is called setting the equations equal to each other because they are both saying y equals yada yada yada. So this is actually like an extra nice and easy example. And you can just take these two right sides, set them equal to each other, and that kind of leads you into, like, that gets you rolling. And again, that is technically the substitution method. All right?